This is All Things Ansys, a podcast from the technical support staff at PADT. Episode 142, Digital Twins for Nuclear Energy Cybersecurity with Ansys partner Flownex and Sandia National Labs, along with news and events from the world of Ansys. Welcome to our little podcast. I'm Eric Miller, one of the three owners here at PADT, and welcome to May. I'm recording this on May 1st from PADT's offices in Tempe, Arizona. It's a Friday and I'm avoiding paperwork I should be doing by working on this podcast. The last couple of weeks have been pretty exciting for those of us who are interested in commercial space, and we want to take some time to talk about that. The Artemis II mission was especially meaningful for me since I'm of the age where I saw Neil Armstrong walk on the moon from the black and white TV, or on the black and white TV, in my grandparents' living room when I was 5. Like a lot of people my age, the mission to the moon was an inspiration for much of what I am today, including my career as an engineer. There's a lot that went into that, and being Legos and Star Trek are up there, but the Apollo missions are a huge part of it as well. So the other thing is that we have customers who have provided components for the mission, and we were involved in some of the additive manufacturing for polymer 3D printing for some of the components on the Orion capsule. Needless to say, Ansys was used all over the rocket, the capsule, the launch systems, the tracking, the communications, the missions, you name it. There's probably some use of Ansys somewhere in one of the components on any part of the entire life cycle of that mission. It's pretty cool stuff. I just wanted to point it out that the Artemis was really, really important. We hope that some of you had a finger in this mission, even a very small one. We are also lucky enough to have done some simulation work for Blue Origin on New Glenn with Ansys Mechanical. So it was pretty sweet to see that beast launch and shake the ground, and even virtual or over the streaming. But to know that we had done some simulation on some of the components in that guy. So very, very cool. Love it. The other thing that happened, of course, is Falcon, SpaceX is launching something, almost every day, sometimes 2 times a day. But the big news was that after an 18-month hiatus, Falcon Heavy launched. And with a tie-in with PADT is that it was the Viasat-3 satellite that was on there. There's a payload. And Viasat-3 is right on the other side of the lake from us in the ASU Research Park here in Tempe. So at least their Arizona operations. And it was really cool to see that. We know a lot of people that worked on that bird, and it's pretty cool. And of course, they use a lot of Ansys, as you would imagine. The other thing that was kind of really nice that we're celebrating about, we can't talk too much about, is that we had another customer, and they did a test here in the Arizona desert of a key function in their system. And they invited one of PADT's employees that they've been working with to come on down to the desert and watch that test. And we supported their Ansys usage internally, as well as doing the overflow simulation work for them. So it's really kind of nice when they invite us out and we get to see the test and make sure everything works okay, and kind of applaud with them when it does. Last but not least, to make it a real spacey month, is that we were at the Space Symposium in Colorado Springs. Hopefully you saw us in the Arizona booth, or some of our folks at the Ansys booth there at Colorado Springs. So pretty cool. We work in a ton of industries, but space holds a special place for us, and hopefully for you as well. And you can join us here at PADT with a celebration of a really, I think, important month when it comes to where we are in space and where we're going. So also, before we get to our main discussion for the day, I wanted to bring up something called Arizona Tech Week. You might not have heard of it if you don't live here, but if you live in one of the big startup communities, the Bay Area, Boston, New York, Los Angeles, they do these startup weeks, which are kind of patterned after Fashion Week, but for startups. And we did our first one here in Arizona, and it was amazing. I don't want to talk too much in depth about it, because our listeners on this podcast tend to not be from startups or not be from Arizona. But I wanted to just let everyone know how explosive the startup growth is in this state, and especially around hardware-based companies. And while the rest of the world is focused on AI, which makes sense, and there's plenty of companies here in Arizona focused on AI, we have a large amount of companies developing the hardware that runs AI, that takes advantage of AI, whether it's a medical device or a defense product or whatever. The electronics and hardware that make up the networks, the antennas, the photonics, and all the stuff that we need to connect the systems that do AI, data center cooling, you name it. And then also the sensors. A lot of our customers work on sensors that provide data for AI. not our customers. I'm sorry. I was thinking about something else. People in the Arizona startup scene. There's quite a few that do sensor-based things. Coatings that could be used to make the computers run more efficiently. There's so much that we do here in the state that is needed to make the AI revolution possible, and to have them all come out was really great. We held an actual hardware startup session. It was 4 hours long in the morning on the second morning of the week, and it was packed. And needless to say, we had people there that were very familiar with simulation. Others were maybe a researcher or an academic who is building a hardware company and weren't familiar with it. They were test bench type people. And it was a great discussion. We spent a lot of time talking about the advantages of simulation to get your startup to funding and scaling faster with less cash burned. And the concept of using virtual prototyping instead of physical testing really resonated with the team. We talked about other stuff as well that's unique to startups, including the very difficult issue of funding the capital costs of building prototypes. But it was really cool. The whole week was great. I had a wonderful time. I saw lots of great people, learned a ton. We have some new customers out of it. It's just been great. So definitely PADT is going to double down in 2027. And if anybody from Arizona is listening, please come down. If you're not from Arizona, please come down. And it's really cool. We love it. Okay, let's get down to business here while we're here, which is usually talking about Ansys and an Ansys product, but we're not going to talk about Ansys this time. We are going to talk about an Ansys partner called Flownex. And if you listened last month, you know that was our commercial. PADT is the North American distributor for the 1D thermal fluids system level code called Flownex. And one of our customers that uses Flownex along with Ansys products is Sandia National Labs. And we asked them to come on because they have implemented an actual digital twin to model the cooling infrastructure in some other thermal fluid systems on a nuclear power plant. And they have this platform that any kind of simulation physics tool or any kind of data can plug into, and then they can actually look at how well it behaves from a reliability and safety standpoint. I think we listened to the interview, so he'll explain it much better than I did. But the point is that what they did with Flownex specifically is something they can do with a lot of different simulation tools, including other Ansys tools. So even if you're not a Flownex user, it's worth listening to because we're going to get more and more into this idea of creating this virtual representation, this digital twin that we then use to do things. And in this case, it's used to do safety analysis, cybersecurity safety analysis, which is pretty cool. So it's really exciting. Let's listen in. Well, today we're going to talk about one of my favorite topics, which is nuclear engineering. And we're lucky enough to be joined by one of our customers from Sandia National Labs to talk about one of my favorite buzzwords, digital twins, and how in the real world, it's not a buzzword, but it's enabling some pretty cool things. So let's do some introductions and we'll get into the meat of it. So, Stuart, why don't you start off, introduce yourself, where you work, what you do?
Yeah, sure. So my name is Andrew Hahn. I work at Sandia National Labs, and my background is all in nuclear engineering and things like space nuclear, things like that. Really deep into ModSim, but my title at Sandia is actually a cybersecurity engineer. So I'm kind of a cross between the cyber side of things as well as the nuclear.
Very cool, which is very important as well. And then we're also joined by some PADT employees to kind of help us out who have worked on this project. So we'll go in alphabetical order, and I'll get your first name right because you only have one, is Miles.
Hi, Miles Adkins. I've been with PADT for about 8 years now. I'm I guess you call it a fluid systems engineer. Degrees in mechanical engineering, but I've been kind of dealing with fluid systems either as like an engineering services role or as a technical support role for the past 8 years, mostly in either the gas turbine space or nuclear kind of systems engineering.
Excellent. Yeah, very cool. And then Molly.
Yeah, so I'm Molly Rhodes. I'm an application and support engineer here at PADT. My background's in mechanical engineering. In school, I primarily focused on structural mechanics, but in the workforce, kind of transitioned into thermal fluid systems engineering. Started out in the aerospace industry and then came to PADT. So under the Ansys suite, I support tools like Ansys Mechanical and Thermal Desktop, but then I also support this 1D CFD tool that we're focusing on today, which is called Flownex.
what a fantastic segue. Because we're this is the All Things Ansys podcast, but we're going to talk about the Ansys partner, Flownex. So, we've been using Flownex and selling Flownex for quite some time now, and we've got customers all over North America. But one of our fastest growing segments is the nuclear industry, and a 1D fluid thermal code just seems to fit really well into that. And we'll talk about that a little bit later, and why whatever 1D thermal code you're using fits into what's going on with this digital twin. But let's go ahead and really start, Andrew, with what is you mentioned cybersecurity and you mentioned infrastructure for nuclear. Let's talk a little bit about the goals of what you're doing.
Yeah, so really, my job has a couple of goals, and they kind of are interrelated. So one of the main things that I do here at the lab is I construct very detailed, high-fidelity digital twins of nuclear systems, and we often call these things systems of systems digital twins, where we're looking not just at the physics, but we're also looking at the control system and the networking that's associated with that control system, and that's so that we can really have an in-depth understanding of the cybersecurity risks inherent within these systems and how they trickle down from really impacting the network to the control system, and then how that causes consequences on the physics systems. But the other sort of branch that I lead is a project called ARCADE, or the Advanced Reactor Cyber Analysis and Development Environment. And its goal is really to fulfill the needs of the NRC Regulation Guide 5.96. And what that actually is that this is a lot of sort of legalese, but it's a guide to fulfill the cybersecurity regulations that are written in 10 CFR Part 53, which is the new licensing guide for non-light water reactors that was just passed by the NRC. Actually, just passed it should be the 28th that I believe it comes into effect. So ARCADE was really meant to be able to fulfill the needs of this regulation guide to allow licensees to more easily license their reactors from a cybersecurity perspective. So I know you had something potentially to say there. I wanted to give you a sec.
No. I'm just agreeing with you. I think it's okay. We're very excited about the fact that I know the feedback we've been getting, Miles, you can correct me if I'm wrong, from our customers is we just need to know what the regulations are going to be, and the fact that it's now been put down is really an important step forward.
Right, and my group was actually sort of instrumental in helping write this regulation guide. And one of the key things behind this is, we want to try to automate as much as possible fulfilling the needs of this regulation. And so the way that we structured this document, it sort of creates what we call a tiered cybersecurity analysis, or we just call it TCA for shorthand. And ARCADE is really the foundation of that. So this is sort of, I know I'm going to use some buzzwords, but it's a risk-informed, performance-based approach. And what that means is that in this tiered approach, we utilize ARCADE to understand the risks that are inherent within a particular system. And then the rest of the tiers respond to those risks. And this really gives the designers a lot of different opportunities and options to mitigate threats in their design. And that opens up a very wide possibility for different types of technologies that they can use. So, in the past, previous regulations such as like Part 52 and Part 50, they were more prescriptive, and they prevented you from using some really novel technologies that are going to be really critical for nuclear in the future. Things like wireless and remote operation and autonomous operation. Those types of things are totally off limits in the previous sort of regulation documents. And so what our regulation guide sort of opens up is that possibility of using that, so long as you provide sufficient evidence that your reactor will maintain its safety. Well, so how do we go about that? Well, what ARCADE does is it actually looks at the physics of a system to help identify unsafe control actions on that system that could lead to a consequence. And so, but we don't really do the physics part, right?
Mhm.
We let the designer plug in their physics simulation into our code, and then Arcade automatically tests it. And one of the key simulators that we have connected to it is actually Flownex. And that's one of the first ones that we plugged into because, well, one, it was something our partners were using, and it was actually really easy to plug into, just the way that it's built. So we do plug into other simulator packages. We're trying to be very agnostic about, what you can bring to the table to plug into Arcade, but definitely Flownex was one of the first that we plugged in, and we have the code to plug it into our system available open source. So it's been sort of a key tool that we've been utilizing in the system. But a little bit more about what does it actually do under the hood, right? So we have our physics package, essentially like a digital twin of the physics of the control system of your reactor, right? Because we need the valves and the knobs and the actuators to be physically modeled in the system. And so that allows Arcade to essentially modify the position of all of these controls within the plant to see what would happen. And that's exactly what it does. It sort of, in a rather brute force manner, it executes all of these different unsafe control action categories on a plant, and then it mixes and matches them. It tries to solve, what sequences of UCAs are going to have a consequence on the plant, and it'll continuously search for this until it's reached the end of what the designer has asked it to do. And at the end of the day, what you get out of it is a report telling you, okay, this area of the plant has concerns, it has safety risks within it. And you can do a couple of things from a cyber perspective. You can either mitigate the threat that presents, within the physics of the system. So, like, let's say I have a valve, and the only time that valve is ever used in normal operations is, between 20 to 60% open. But when an attacker uses it, they always turn it to 100% open in order to cause a threat. Well, if I redesign that valve so it limits its flow rate into an acceptable regime, now I've solved the threat. And I've not just solved it for cybersecurity, I've solved it for safety. And now you have a whole thread of activities you no longer have to do from a cyber perspective. And potentially a safety perspective as well from the licensing front. Now, the other option, of course, is, let's say you identify a system within the plant that is risky, but there's no way to mitigate it. Like it's really hard to mitigate the risks presented from, say, your control rods, right?
Right.
Well, then you can basically score the risk to your facility and identify, what are the appropriate cybersecurity controls that should be applied to maintain its safety. And that's sort of what the TCA sets up for you, is you identify the risk, you make engineering decisions, and then you can decide to mitigate these things with cybersecurity controls. But it really ensures that you're focusing only on the pieces of the plant that actually matter to the safety and security of your facility, right? And that, one, it reduces cost across the board massively, but it also ensures that you are focused on the things that matter, and you can exclude all the things that don't. My soda machine down the hall doesn't need to be a critical digital asset anymore, right? Like, we can exclude a lot of things on, like, your tertiary side or your secondary side that don't really have an impact on the radiological safety of your plant. And that's a really big deal. And you can see how this readily, it doesn't just apply to cybersecurity, which is its main intent. It really applies to safety across the board. And that's sort of the critical impact we're looking for. And being able to automate all that is really powerful. And so, but this, again, when I'm going to bring it back down to the physics aspect of this, is it's really critical to have a physics system or a physics simulator that can be qualified, right? Something that is accurate and that you can validate that it's accurate, right? So if I just, and I am one to do this, if I just cook up something in like another kind of toy simulator package and I try to qualify something with it, it's very you know, credulous. I'm credulous about the reasonability of the results, right? And so having a physics package, something like Flownex that allows you to have a highly accurate model is essential in being able to do these types of analyses. So, that's sort of
Cool.
in a nutshell what we're doing.
What I love about that is, in my earlier career, we would do the physics and we throw it over the wall. I'd have no idea how people on the safety, and of course we didn't have cybersecurity safety back then, but it's on the safety side of things, used that data, right? It's great to see the merger of simulation into the safety realm, but both physical and cyber. It's really a great advance. So Miles or Molly, I think one of the enabling technologies in a tool like Flownex is that open interface. Can you talk about how you hook, whether you're doing a nuclear reactor or a secondary flow in a turbine engine or some sort of a water treatment plant? How would you, to use it as a digital twin, how do you hook it up?
So, it all depends on the use case. But I think that, as far as kind of controls integration, folks are typically using OPC UA as the client. Which basically how it works is you can set up a live connection between your simulated model of your plant and physical assets. So that could be reading in real-time sensor data from an actual plant and adjusting your simulated model to be a more accurate representation of the conditions in that plant, so that you can kind of predict performance, or set up situations for doing planned maintenance, things like that. The other way that it can be connected, and I think this is where we are with the arcade program a little bit, is doing hardware in the loop. So if we have our control scheme already set up, we have physical controllers that are changing positions of valves. I think Andrew mentioned control rods being very, very safety critical, right? And I'm thinking in my head as Andrew's talking about like how if the the position of the control rod reported to the operator is different than the actual position, I can imagine these being those kind of scenarios where understanding whether or not the passive control schemes or whether redundant mechanisms are in place to kind of ensure safety in those kind of situations. And in this case, where you're tying, a physical control scheme into Flownex, I imagine you could test kind of different scenarios or push malicious code onto a PLC and then see, rather than testing on a physical plant, you could see the system response of the thermal hydraulic model with integrated, point kinetics for neutronics, and see how your plant is anticipated to respond, but physics based, right?
Right.
Is that kind of answer your questions?
And just a little bit more into the mechanics of it. I mean, is it through Python? Is it through Visual Basic? Is it you sending files back and forth? What's the mechanics of the actual connection to a tool like they're using?
So I mean, it can be a text file where you're just writing inputs and outputs and exchanging them over some network location that's visible to both softwares, or both the software and the hardware. I think that some of the faster data transfer may be something where it's like held in memory. But I'm not the computer scientist, so I can't speak to it with a high degree of accuracy. Got to throw some asterisks there, but yeah, in general, it's some sort of some text file, but I think typical control schemes, softwares interface with that OPC UA or OPC server connection.
Okay.
There is, native scripting in Flownex is typically in C#, although there is options for Python integration and through API calls. The world is your oyster.
Okay.
With setting up connections between the simulation software and any kind of third-party software that I think runs on it's got to be on a .NET framework. But Andrew might even know more about that than me at this point.
I was going to say, so Andrew, you went through this in your specific application. What was the
Yeah.
mechanics by which you hooked it up?
Oh, see, and I can't answer this because I was really deep in the weeds on this. So, and this is something that I really love is that because I was able to use C#,
Great.
I
Yes.
had a lot of opportunities to do things the way I wanted to, rather than there's some other simulators I've integrated with that you're really locked into a box. But anyway, the way that we connected all of our systems to Arcade is actually through shared memory or memory mapped files. So we wanted a really low latency connection so that we could simulate events that have essentially no latency. So all of our UCA simulations essentially have the benefit of not having any latency built into them, which it can be very interesting or very valuable when you're trying to understand timing mechanisms between multiple UCA events. And being accurate on when you execute a UCA time-wise within a simulation. So, but the other cool thing, and Miles, you may not know about this yet because it's something I don't think we've really talked about, is that Arcade, like I talked before about some of the digital twin efforts that we're working on. We actually utilize Arcade to integrate with hardware in the loop using our low latency memory connections. So and we've been really trying to push the bar for having low trip response loop times on our hardware in the loop. And so we've actually developed an entire system in our laboratory. We call it the Equipment Test and Evaluation Laboratory, where we're able to connect Arcade to hardware in the loop, and we simulate the digital and analog I/O going into that piece of hardware, and then we also simulate its network connection as well. And the concept is we want it to believe that it is in the plant that we are simulating, and then we can do all sorts of different experiments on it, from seeing how it reacts to different sort of UCA events. We can see how the actual hardware could be hacked or manipulated in real life, and it also gives us a couple of other opportunities to do things like, especially as we're talking with other partners in the industry, is this is a capability that you could use for doing engineering on the actual hardware. So, figuring out how am I going to program this PLC, right? Exactly. And then doing burn-in testing on, a highly instrumented system like this, where you've basically simulated the environment that this controller is going to live in. And we're also thinking about, there's like FPGA systems, especially safety systems that the nuclear industry wants to use, that would not be really easy to simulate. And so our idea was, well, why don't we just have it as hardware in the loop and then simulate all of its signals, and then Arcade can still do its UCA evaluation, but with this hardware in the loop added. And that way we can really get a solid understanding of how that hardware would handle all these different safety situations that we would throw at it. It becomes a really useful tool for designers, essentially. But again, we're really leveraging off of that shared memory or memory mapped implementation with Arcade in the simulators as well. It takes a little bit of effort, but we get a lot of value out of it. At the end of the day, the low latency stuff, I have to mention it's not really super critical for these high inertia systems like,
Mm,
big giant pumps in a
hmm.
conventional reactor. But where it starts to get really, really useful is when you're talking about low inertia sorts of systems like turbines. And
Okay.
it's especially important when you start thinking about, okay, well, I want to use something like a closed or a Brayton cycle supercritical CO2 system as part of my reactor's energy conversion. Well, that's something that you wouldn't be able to hardware in the loop test on
Hmm.
conventional systems, but utilizing this with this incredibly low latency, you'd be able to test the controllers for your turbine on this.
So I came to this discussion thinking about low latency as far as, send a request over, get an answer, but shared memory kind of opened my mind there. You're in the hardware in the loop, you're emulating the hardware from that level, not
Mhm.
like abstracting it. It's in there. That's really, really interesting. I love that. Oh, that's so cool. Um, Molly, do you have anything to add to any of that? There's a lot of modeling that goes into building these models. I mean, if somebody's thinking about doing this for their plant, what's important to make sure you've got a model that you can use this way in a tool like Flownex?
I would say just understanding your system parameters is probably the most important part.
Hmm.
Um, like I think Arcade is really cool because once you build out that system, you can simulate all kinds of conditions. And I think that's probably the most important part just for safety analysis. So I think the work that Andrew is doing is so cool. I'm
Yeah.
really excited to see what they're doing.
I didn't think I'd get this excited about hardware in the loop testing, but it is super cool, right? Because you're
Yeah,
not designing your model to do a certain scenario. You're designing your model to act like the real thing. So no matter what
Right.
scenario you throw at it, it reacts properly.
exactly.
Physics informed. Yeah.
Hmm. Hmm.
That's right.
Hmm. That's so cool. So what was the biggest challenge you faced? And not necessarily, well, let's just stick with the hooking up the simulation tools, Flownex and others. I mean, what was the biggest challenge in getting them connected into your arcade system?
Um, you know, Honestly, of course, the biggest issue with doing these types of connections, there's kind of two that I can really think of
Hmm.
that are critical. One is establishing that shared memory link, and that's different depending on the type of
Hmm.
simulator you're talking about,
Right.
what it can handle, as well as just the type of programming language that is used within it. So that's a high dependency issue right there, and depending on whether you're in Linux or Windows changes things. So,
Mhm.
there's a lot of intricacy there. So that's a big leap. But the next one is actually interacting with the components inside of the simulator and also doing things like timing control.
Hmm.
So, there's the import export of data externally into your simulator, but there's also things like, well, can I stop the clock for my simulator and then wait for a response from the rest of the system? Like my hardware in the loop or the UCA simulator, or things like that. So being able to control the simulator internally is also something really critical that you need to be able to do. And so having an API that allows you a lot of this flexibility and control is essential.
Yeah. Okay. Very, very important. Yeah. Um, that is just, yeah. So you got me thinking about all sorts of things. Um, the are I guess so I've seen people do digital twins where they actually model the control panel itself, the user interface for the human side. Do you guys do that as well?
So we have the capability of doing it. We commonly will do like SCADA interfaces for some of these systems, but it's not a high area of focus for us because, and we might simulate the connection to it, right? How it communicates and things like that. But we haven't done a huge amount of human in the loop testing. That's
Hmm.
something that we're looking into. We do have an entire human factors team here at Sandia, and that's something that we would like to investigate with them in the future because we think that a lot of cybersecurity is really crosses over into the human factors parts of things, especially when you're relying on an operator to perform an action and maybe they're lied to, right? But that's an area of research we haven't necessarily touched on. We have the capability though. But right now we're looking at a lot, especially in our system of systems digital models, is really how does an adversary traverse a network in a plant and then cause consequence and then
Gotcha.
measuring that consequence. And that's the physics key there is measuring consequence.
Okay, cool. That's right. Because I was backing into operator and not cyber. Yeah, I get it. I get it. That's really cool. Molly or Miles, do you guys have any other questions before we kind of wrap it up?
So I see why this is going to be really important for folks who are developing the next generation of reactors and things like this. But I also see this as it really kind of blurs the gap between simulation and test, because we're not just simulating the system, we're actually putting physical assets into that model. Do you see this as something that would be like a living tool to accompany your physical plant? I imagine as technology develops, risks change and different kind of especially as it we talk about like AI and cybersecurity, and I read some headline the other day about the new Claude model being like really good at breaching different like firewalls and causing security havoc. So I guess it's half a question, half a statement, that I can imagine that as someone operating one of these reactor plants, you would almost want to keep this thing going indefinitely, so that as new risks are coming out and as they become understood, you can keep qualifying and making improvements where needed to accommodate these new hazards.
Miles, you're absolutely right. So, and there's sort of two sides to this coin, and one is that so the way that we've set up the TCA, the concept is we're hoping to avoid as much as possible doing reevaluations, right? So we want you to design the physics of your reactor to be inherently secure, but there's always going to be pieces that aren't, right? And so it would be in the best interests of the entity to be able to retest their hardware, their software, things when they update the plant, right? That's one of the things current generation plants are facing, is that their previous hardware that they qualified their license with is no longer being manufactured, and then at this point in time, it can no longer be maintained, and so they have to go through a lot of effort to requalify digital systems for their plant. And it's like, well, if we consider the current, or the future advanced fleet, and you think some of these reactors are going to be operating for like 60 or 80 years, well, technology will change, and they will have to keep up at least some representative, like, digital twin, whatever you want to call it, model of their facility to be able to requalify systems on it. That would be sort of ideal for them to maintain one of these for the long term. It also gives you an opportunity. There's a lot of fringe benefits, like you can train operators on it, you can train engineers on it, right? So it's not just a tool for licensing per se, but it's also a tool for ensuring that your staff know how to operate and maintain this reactor for 80 years, right?
Right. No, that's fantastic. Makes sense.
It's so cool. Okay, we can keep talking about this anymore. Molly, do you have anything to add before we wrap it up?
I was kind of curious about how Arcade is open source. Andrew, would you mind talking about that a little bit? I think it's cool that it's open source, but just kind of curious how that came to be.
Oh, well, it's interesting. You touched on a complicated sort of subject for Arcade right now. So the majority of it is open source. So the ability to create a digital twin, do the hardware in the loop, all that stuff is open source, as well as being able to do unsafe control action executions. But currently, we have the automated side of it, the automated system that identifies those sequences of UCAs is not currently open source, and we're working on licensing that. The idea there is that we wanted to sort of protect that technology, as you can imagine that if a cyber adversary had a model of your plant, they could use our tool against it. And we don't want that to occur. And so we want to control that analysis piece a little bit more. But that's something that we're opening up to like universities and other select industry partners so that they can utilize. And we can also improve the tool as they start using it. That's currently how we're working on this. And in the future, we're hoping to be able to open it up a little bit more. But for now, it's something we want to that piece of it to control just a little bit more, so it doesn't fall into the wrong hands, you know?
Yeah, that makes sense.
Very cool. Very cool. All right. Well, this is really fascinating. Hopefully, one, if you're interested in where things are going from a nuclear regulatory standpoint and the advances that are being made in that industry, you've learned a lot. If you're interested in plugging in physics simulation hardware in the loop even into your systems, it's a very doable thing. It's a pretty cool thing. And I think the thing, my big takeaway is how important latency is, or low latency is. And, I was focused on we use a 1D tool because it's really fast, but also you need access to that shared memory as well to get it even faster. So big takeaway for me there. I really appreciate it. Thanks a lot, guys. Hopefully we'll have another discussion in the future about how you're doing more with this tool.
Sounds great. Appreciate you having me on.
Yeah, thanks. Thanks, everybody.
Cheers.
That was really good. Thank you. Thank you so much. I learned a ton.
Good.
Yeah.
Go ahead.
Yeah. Really
yeah,
interesting. I came into it totally not thinking about hardware in the loop. It's just fascinating that you can do that now.
Oh yeah. I mean, and you'll see in the next couple of years, this thing will evolve, and well, it depends on next year, right? We could be the dog that caught the car, and we got to figure out how to drive it because we have too much funding support. But that's not a bad problem to have. So
yeah.
This thing is going to change very rapidly, and there will be absolutely stuff to talk about in the future, especially as we look towards doing licensing applications with it.
Very
so
cool. Can't wait to see that. It'll be a great day. Yeah. Well, thank you so much for coming on.
Hey, no
our
worries.
listeners love it when a user comes on and talks about what they're doing. It's so fascinating.
Yeah, absolutely. Always glad to. Anytime, just hit me up. You see some arcade stuff in the news or publication somewhere, and you want to reach out again, I'm always happy to talk. So
great. Excellent. Love it. All right.
Cool.
Thanks much.
All right, well, thank you. All right.
Have a great weekend.
Okay, as mentioned in the beginning, digital twin is a big buzzword, and right now, and it's kind of tough to find, people that are willing to talk about how they're actually using it in their world, and finding a value-added application like this really brings home the power of the approach, and how virtual prototyping can be used in such a cool way. And instead of just doing analysis for the sake of analysis, it's a tool that feeds something else. In this case, the safety analysis. So please reach out to us at info@padtinc.com or 480-813-4884 if you want to learn more about Flownex, which hopefully you got a little taste of that as well, or how to do digital twins with Ansys products, which leads us to our commercial, right? And well, you probably guessed we're going to talk about Flownex, but as I mentioned before, that was last month's ad, not very good planning. So instead, I'm going to focus on the second thing I just talked about, which is implementing some of this stuff. So really think about hiring PADT to help you implement your simulation-centric digital twin strategy. So digital twins can be created using data or simulations. And if your application is going to rely on physics modeling, PADT is your partner because we understand the simulation side. We understand programming. We understand how to put things together. We understand system-level modeling. And we know how to create something that can be used from a parameterization standpoint as a digital twin, even at a system level. You can do direct coupling or at a system level model. So really cool stuff. We really love doing it. We can start really small with a little phase 0 discovery and figure out how we can get you a usable digital twin. What are you trying to do with the digital twin, and what kind of a simulation do you need to get there, and plan it out. And then we can grow from there. You can do part of the work. We can do part of the work. You can do all of it, whatever you need to get there. So it's really exciting. It works. We saw an example of it just now. So maybe it's time, if you haven't in a while, to sit down and take a look at creating your digital twins, whether it's to train your AI models or to do predictive analytics, or if it's to debug an issue. It's pretty neat stuff. So reach out. Same places I mentioned before, info@padtinc.com, or our phone number at 480-813-4884. Let's get on a call and brainstorm some stuff. So moving into news and stock. In the world of Synopsys stock, some good news there. I'm starting to get my head around that stock. It's SNPS. After spending how many decades following the ANSS stock, it's taken me a little while to understand, what do the investors care about, right? They all care about someone else thinking the stock price is going to grow, right? That's how the stock markets work. But I'm starting to get my head around it. So we'll get into it a little bit more than we have in the past. So if you remember when we last talked on our last podcast, the shares have been lingering at around $400 a share. It dropped down to actually $383 at the end of March since the last podcast. And then it started to climb enough to be up year to date 1.8% on May 1st. And up 23% from April 1st to May 1st. So that's significant, a 23% gain from April 1st to May 1st. The analysts are excited and are reading some articles. Yeah, that's what kind of drives it. One of the big things that happened is that an activist investor decided to increase their ownership in a significant way in Synopsys stock. So that was a signal for other people to buy. But I want to know that can't be all of it. So digging in a little bit deeper, I found a site called Simply Wall Street, and they kind of summarize stuff. If you give them your email address, you can read it. And they mentioned that the Ansys acquisition, because I wanted to really know how is Ansys affecting the stock. And one of the things they talked about that I guess had been reported in a couple of places is that the team had predicted a $400 million cost over 3 years to integrate Ansys into Synopsys. That's going really well. They think it's going to get done faster than that, so they won't have that cost in a little bit. So that's driving the price, and also that it's moving faster. Those workflows are moving faster. They also think there will be they predicted that they'd save $1 billion per year through synergies as the organization merges, and that's looking to be true. In fact, there may be more. So we'll have to keep our eye on that. And the big long-term concern out there in the world of finance is that they took on a lot of debt to buy Ansys. That $30-something billion wasn't cheap. They had to borrow it from somewhere, and that's been a concern, right? It's a lot of leverage. Now they're starting to see that things are going well, numbers are looking good, and they might be able to pay that debt down a little bit faster. So that was another thing that drove it up. And I think also reading through the articles, I don't know how much actual investors understand this, but we'll talk about it when we get to Ansys news. There was an entirely new release of the software suite, both legacy Ansys and legacy Synopsys, and there was a lot of integration of Ansys into the Synopsys toolset. So physics modeling to help with the silicon modeling. And they also had some cool announcements with some of their bigger customers that made people think, hey, things are going pretty well over there. So that's why the stock is up. We'll definitely get together again in a month or so and see where it is. Maybe it'll go up, maybe it'll go down. I'm not good at predicting these things. I'm trying to understand them, but I don't predict them. And also, depending on when we do the podcast, maybe the second quarter investors call will be over and their finances will be out. We'll go over those. If so, if not, we'll get into the next one. So there wasn't a lot of Ansys news. I'm starting to suspect that the Synopsys PR team is not quite as vocal. So we'll see. We'll see how it goes. Most of their news is around some partnership with some fab somewhere in the world for silicon side of things. But we'll keep it going. The big news, the multiple articles, was the same as I talked about when we started this podcast. The Artemis mission, it's amazing. They wrote some stuff in the news, or their news releases, about how Ansys was used on some of the key systems in that launch, including, I think, the spacesuit is the big focus of the press release. So it's a big deal. And then on the Synopsys side of things, this is really important too, and I kind of mentioned it. It probably helped drive up the stock price a little bit. Is they released a workflow that supports TSMC's most advanced process and packaging nodes, and that's these really small ones. It's like 3 nanometer and 2 nanometer width, which is just insane. What makes this announcement special is the amount of practical AI built into the design flow. So they're integrating Ansys in there. They're integrating more. I mean, if you've ever been in the semiconductor design space, where they design the chips, there's always been a lot of AI in there, especially rules type stuff. But they're really doubling down on some of this new AI technology within the Synopsys side of things. And it's really exciting to see them this quickly release something that the industry seems to be happy about. So new product that's got some really cool capability in it and makes things run faster, et cetera, et cetera. So yeah, that's the Ansys news. We'll see what happens since the next time. We don't have any. I can't complain about Ansys not having a lot of news because we don't have any either. I mean, the big news for us, the thing that's doing the best for us on LinkedIn is after years of having a faded sign out front of our building here in the Tempe Research Park, and the tenants on the sign haven't been gone for a while, we finally made it a priority to get a new sign. We have sort of a bright, shiny new sign with nice black lettering for PADT owns the building that we operate out of here in Tempe. We use about half of it, and then we sublet the other suites to other people. So we have a electronics test company called CMC Labs that is next to us, and then next to that is PADT's spin-out called Oryx. We make additive manufacturing post-processing systems. Next to them is a company called Purity Resource, which does water purification from the semiconductor industry. And our newest tenant, this is worth a news release, is a company called Scienta, that is an Australian company that has a unique metallization technology for making interposers in 3D and 2.5D chip packages. And if you do go to the Ansys/Synopsys websites, you'll see them talking quite a bit about 2D, 2.5D, and 3D packaging and how we model that with those tools. And so it's kind of neat to have somebody in here that's got a new and revolutionary way of making those components. So kind of exciting. So glad to have them in the building. Glad to have a new sign. I hopefully will replace it sooner before it fades again. The Arizona sun can do that. So I like to pick out 3 things in the Ansys blog worth sharing that I think are worth sharing, and I found 3 ones. So it's blog.ansys.com. And the first is called HEN Technologies Optimizes Firefighting with Multiphysics Simulations. And they've been a customer for a while, this company, HEN Technologies, or I don't know if it's HEN or HEN Technologies. And they make the nozzles the firefighters hold. They make the valves. It's a pretty complicated CFD problem and a really important one to solve properly, because there's that thrust, there's what does the spray look like? Anyway, you can read the article. And it was just a cool use of CFD. They used both Ansys Fluid and Ansys CFX to do the nozzles and the valves. And it's a really real world application that hopefully will never be involved in your life. But I found it very, very interesting. The next one was called Customized Pump Design with Simulation and AI. And so with everything in AI these days, I thought that was a really good article to kind of show you. It kind of goes through a comprehensive, how to use Ansys Suite to model the various things in a pump, a water pump per se, or some sort of fluid pump. And they do that, but they also talk about how AI fits into that. So it's a nice look at that, something that you could use today. And then the last is connecting the dots, transforming quantum computing with photonics and simulation. And, AI has sucked all the air out of the room. How many times have I mentioned it so far in this podcast? And we forgot that another area going through a significant transformation and improvement is quantum computing, moving from the academic maybe to the actual real. And it touches all sorts of physics. We have a couple of quantum computing customers. This particular article that I mentioned, the title of Connecting the Dots, talks about one specific customer. I think that's one of CAD-FEM's customers, and how they're using it. It's very similar to what our customers are doing. So it touches on all sorts of physics, and electromagnetics, and photonics included, some thermal. And the other thing that's kind of neat that appeals to me, and based upon where people click on our website, a lot of you, is where using Python to automate it. So it's a good article. Take a look at it. If you're not doing quantum computing, take a look. So let me open up the PADT blog, because we've had quite a bit of cool articles written since our last podcast. The team is having a good time sharing some tech support things. Where's was the last podcast? So we put out a newsletter since then. There it is. Okay. So basically, what we did is take a look at a couple different areas, a couple different tech support calls, and turn them into articles. So the first one was by Alex Grisham, and it's called Performing. No, I take that back. The first one is from Cynthia De La Rosa, and she goes into Ansys ZMax Optics Studio 2026 R1 and her opinion of those. And then Alex did a really cool analysis of a thin wall tube, a thin wall metal tube, buckling. So think of stepping on a Coke can, right? This is something we've always done in LS Dyna. LS Dyna is really good at this, but he actually shows how to do it in Ansys Mechanical in using the implicit solver. So it's got a large deflection, plasticity, and contacts. It's got mesh distortion. It's called a post-buckling simulation of a thin-walled cylinder. Definitely check that out. It's got a cool video as well of the thing crushing. The other one is something that Daniel Chaparro did called Saving and Exiting Ansys Fluent when running in batch mode. And the reason why I hesitated there is the picture I picked for that article is of the Mars, the helicopter on Mars, if anybody remembers that. It's a CFD run. And so I was like, what does this have to do with that? It's nothing. It's just a cool picture made of a simulation in Fluent. But yeah, it's a little tricky. How do you exit when running in batch mode with your files intact? And so he goes through that. Then Molly Rhodes, who is becoming our Ansys Thermal Desktop expert. If you don't know Ansys Thermal Desktop, it is a thermal tool, thermal fluid tool that was acquired by Ansys a bunch of years back now. It's used quite a bit in the satellite industry and in some of the process and factories. It's a really, really nice tool. And I'm glad that Ansys brought it in and Molly's learning it. So it's really, how do you get a mesh in there, right? Because it's a finite difference code. It's not a finite element code. So she goes over that. It's kind of neat. The last one that someone put out since then was John Elias, who's new to PADT, did an article called Flownex Simulation. He's one of the Flownex guys. Flownex Simulation Environment, new feature highlight, custom reactor zone colors. So we do a lot of nuclear with Flownex. A lot of our customers are nuclear reactor companies. And so this is something specific to modeling a nuclear reactor in Flownex. And it's very colorful, as the name implies. So take a look at that when you get a chance. Popping over to events. What do we got coming up here at PADT and events? So it's May. The big thing is a couple of webinars that Ansys is actually holding, but we're promoting them. We got Enhancing Optical System Performance with Ansys OptiSlang and Ansys ZMax Optics Studio. Then on the 7th, we've got Calibrate Simulation to Test Data with Ansys OptiSlang. On the 8th, one of my favorites is coming up is a look at what's new in Ansys LS Dyna R1, which is useful. And then getting started with Ansys Fluent. So this is for new users of Ansys Fluent. How do you get going there? And then the last is in the photonics area. And it's really, they're giving a seminar on miniaturization and photonic integration across industries. So pretty good. What are we doing here in the real world? Well, the big thing in May for us is we are one of the major forces behind the 2026 Arizona Manufacturing Showcase. So this is the first time that the Arizona Technology Council has hosted a trade show for the manufacturing sector within the state. We don't really have anything for manufacturing. So PADT and some other companies got together with the Arizona Technology Council and said, let's do an event. And so we'll be there. We'll be showing Ansys. We'll be showing Rapid Fusion, large 3D printer. We'll be talking about all sorts of stuff. We'll be talking about our additive manufacturing, our design capabilities. And I am going to be your host. So May 13th at GCU here in Phoenix, Arizona, 12:45 to 4 p.m. Check out our website for more information. And that's it. In June, we'll be at the E-Mobility and Clean Energy Summit, which is going to be in Scottsdale here in Phoenix. And then I'll be up at the CEO retreat for the Arizona Technology Council in August in Prescott to get out of the heat. And then we got some other events through the end of the year. We'll go over to the next podcast. So anyway, lots going on. That's it for this one. Really hope you enjoyed that look at digital twins. It really kind of opened my eyes to what we can do. And we'll put some more information about that in the links, I think. But don't forget to subscribe to our newsletter, www.padtinc.com/opt-in. Do subscribe and like this podcast, and do spread the word about it so we get some more folks listening. And as always, don't hesitate to reach out. Thank you for joining us for the All Things Ansys podcast, episode 142. As a reminder, this podcast is not affiliated in any way with Synopsys, and the opinions expressed are those of the people on the show only and not of their current or former employers. For more information, visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.